Hi, today we're going to talk about section 4.3 from your book, connecting the first derivative of f and second derivative of f with the graph of f. We're going to talk about the first derivative test for a local extrema. We're going to talk about concavity, points of inflection, second derivative tests for local extrema, and learning about functions from derivatives. So if we look at this graph, we can look and say, okay, it makes sense what an absolute minimum is. The absolute minimum is the smallest point on this function. So this function f is defined from a to b. Over here, if we look over at b, that's a minimum, but it's not the absolute minimum for the whole function. The absolute maximum, where is it? Hopefully you pointed here at C4. That's where the absolute max is. We're going to look at all kinds of different points on here. We're going to look at, okay, this is going up and curving up, so it's concave up. About here it switches from concave up to concave down. Okay. Here it hits a slope of 0, but then it goes back up, so there's no, because it didn't go down, when f prime equals 0, it's not a local extreme value. But on the next value at C2, it is going up and then going back down. So the slope is 0, but because f prime is greater than 0, meaning it has a positive slope, and then f prime is less than 0, meaning it has a negative slope, that would be one of the ways we're going to define a local maximum. And just the opposite for local minimum. Here we have a negative slope and then it goes to a positive slope. So right there where the slope is equal to 0 is a local minimum. You can see if you do that anyway, though, if you switch from, it doesn't have to switch nicely. Right here we have a maximum. It happens to be the absolute max, but it doesn't necessarily have to be the absolute max where this happens. You have a slope, a positive slope that instantly switches to a negative slope. Alright, f prime actually does not exist there. F prime is undefined because the slope from the left doesn't equal the slope from the right. But because it does change sign, that is a maximum since it's going from positive slope to a negative slope. You can see another one that does not have that extreme value there. So it's going from a negative slope and staying a negative slope down to that minimum. Okay, so that's kind of some of the things we're going to talk about throughout this. Again, we talked about concavity. This would be concave down. This would be concave up. Where they switch about in the middle here is called a point of inflection. Alright, we're going to talk about maxes and mins. Okay, the first derivative test is what we just talked about, where if the slope switches from a positive slope to a negative slope, then it is a local max. So you can see that on both of these. If the slope equation changes from a negative to a positive, like on both of these, that's a local minimum. If the sign does not change, the slope is positive here and it stays positive, that is no extreme value here. It is a critical point, I guess you'd call it, but it does not change there. This one's going from concave down to concave up, so it is a critical point, but there's no extreme value. Here, it's got a critical point again, but it is not an extreme value. Okay, at a left endpoint, if the slope is negative on a left endpoint, you have a local max. If the slope is positive, you have a local min. At the right endpoint, if the slope is negative, you have a minimum. If the slope is positive, you have a maximum. Alright, use the first derivative test to find any extreme values and identify any absolute extrema. So the first derivative test says that if we take the derivatives and they're equal to 0 or they change from a positive to a negative, so we want to find the zeros and then we'll test on each side of them to see what happens. It will tell us if there's an extreme value. So take the derivative, set it equal to 0, find those zeros, and then we'll test them. Hit pause. Okay, hopefully you took the derivative and you got negative 6x squared plus 12x, and you set that equal to 0. So we can take out a negative 6x from both of these, leaving us an x and a minus 2 equals 0. So we know that at x equals 0 and x equals 2, we would get 0 there. So those are our 2 points we're going to test. We need to test a little to the right and a little to the left. So let's just make a table and test out our values here. We're going to test at negative 1, that's just to the left of 0. We're going to test at 1, just to the right of 0, and to the left of 2, and then just to the right of 2 we'll test at 3. So we'll test these 3 values and see what happens. So let's take a look at this. We really just want to be, since this is the first derivative test, we just want to be looking at what is f prime equal to here. So at negative 1, we're going to plug that negative 1 into our derivative, and we get negative 1 squared is 1 times negative 6 is negative 6. 12 times negative 1 is negative 12, so that's negative 18. We plug in a 1 there, we'll get a, let's see, 6, and then if we plug in 3, we get negative 18. So the first derivative is negative, switches from negative to a positive. Alright, so we have a negative slope switching to a positive slope at 0. That would be our local minimum. A negative slope to a positive slope, that's a local minimum. At 2 we have a positive slope switching to a negative slope at 2, where the slope is equal to 0. We have a maximum. If you just think about this graph, it is a cubic function and it's negative, so it goes down, up, down, which there at 0 we'd have that. Here at 2 we'd have that value. Yep, so a local minimum and a local maximum. Okay, we also want to be able to test concavity. So concave up is when the derivative, or the slope, is increasing. So here if we look at a concave up, we've got a negative slope that's getting less and less negative till it hits 0, so it's increasing, and then goes from 0 to more and more positive, so it's still increasing. That whole way where it's concave up, the slope is increasing. Concave down, just the opposite. It's going from a steep positive, lower and lower and lower till it hits 0. Then it gets more and more negative as you go. The, I think, easier way to think of this is, where is the second derivative? If the first derivative is increasing, that means the second derivative is positive. Where is it positive? That's the second derivative is positive, is concave up. Where the second derivative is negative is concave down. So an easy test, and you just have to remember it. Okay, use the concavity test to determine the intervals in which the graph of the function is concave up, and when is it concave down. So I kind of forgot to record, so this is the second time I'm talking to my iPad, but the work all recorded for me, so I'm just going to talk you through the work versus you hitting pause and trying it on your own. But if you want to, look away, hit pause, and try this on your own. See how you do. Okay, so here's the first derivative, here's the second derivative. Concavity test says when the second derivative is positive, it's concave up. When it's negative, it's concave down, so I need to test the points. I found over here by factoring the second derivative and setting it equal to 0. This is where my second derivative is equal to 0 at 0 and 2, just like on the last one. Then I tested points to the left and to the right. So to the left of 0, it's negative. To the right of 0 and to the left of 2, it's positive. And then to the right of 2, it's negative. How you'd write that is it's concave down from negative infinity to 0 and from 2 to positive infinity, and concave up from 0 to 2. So I drew what a fourth degree polynomial would look like, a negative with that negative leading coefficient. So that would make sense there. Here at about 0, this is concave down until it gets to about there, where it reaches a point of inflection, and it changes from a concave down, which would be a second derivative that's negative, to concave up, where the second derivative is positive. Then it hits another point of inflection at 2, and it becomes, second derivative goes from being positive to the second derivative is negative. So that is using the concavity test. Now, be very careful. A lot of people will say, well, what you really did is you found out where is it equal to 0, and those are your points of inflection. Well, no. Point of inflection is where it changes from a second derivative being negative to a second derivative being positive. That's the definition that we use. Not always where it's 0 does that work, and here's a couple examples. So it's a caution. The second derivative can be a 0 at a non-inflection point. Okay, if you look at the function x to the fourth, that looks like this. This is at 0. Well, the second derivative is 0 there, but that's not a point of inflection. That's actually a minimum. So that's a good example of one that doesn't work there. The second derivative, where it's not equal to 0, okay, the x cubed, it should be a little steeper than this. Sorry, it just didn't draw very well. It should look probably closer to like that. Where here, alright, you take the second derivative, it doesn't exist. But it actually is a point of inflection. It changes. The second derivative does change from positive to negative there, so it's a point of inflection. So just be careful the way that you use that second derivative. It's not where it's equal to 0, it's where it changes from positive to negative or from negative to positive. That's a point of inflection. Okay, find all points of inflection. So we kind of already did this one. So you can try it if you want, but we basically did the same equation. It was just in a different form, so I wouldn't waste your time. Now, I do want you to take these, I want you to graph the position equation here on your calculator, and then just try to draw it as accurately as you can. Alright, or maybe, don't do it that way. Go ahead and hit pause and use what you know. We want to find a maximum and a minimum. We want to find a point of inflection. We want to find where it's concave up and concave down. So go ahead and try to graph this position function just using what you know about the first derivative test and second derivative tests and what you can kind of plug in. Then after that, I want you to take out your calculator, plug that into your calculator, see if you get it to match. Then after that, I would like you to graph the derivative there, which would be the velocity, and then I want you to graph the second derivative there, which would be the acceleration. So a lot to do. Hit pause, give it a shot. Okay, if I was going to do this, the first thing that I would do is take the derivative. So v of t is the derivative of position, is equal to 3t squared minus 46t plus 120. And I would set that equal to 0. Factor out, let's see, can I factor something out of this? I cannot really factor this, so I'd have to use the quadratic. So if I'm trying to find where is this equal to 0, where is my second derivative equal to 0, that will tell me my mins and maxes. Well, not always, we got to test them and see. But just do the quadratic and find those values. So at about 3.4 and 12, those have slopes of 0, or the slope equation is equal to 0, so the slope is 0 at those points. If you test a point that's to the left of 3.4, that would be at 3. You get a, well, I want to actually test it right there just so I can get what is my maximum or minimum. That should tell me enough about what we need to know there. So go ahead and try to plot that on there as best as you can. Take the second derivative and use that to see if it makes sense for the concavity, and then graph them on your calculator to see what they look like. I'm going to switch to the next screen that should show these graphs much nicer than I can draw by hand. So here's what they actually look like. If you look there again at that, I don't know what that was, like 3 point something, 3.2, 3.3, 3.4. We hit that maximum value. If you look down here at the velocity equation, that is where the velocity is equal to 0. We go over to this 12 here. At 12, that's where it's equal to 0. Okay, we want to say, okay, it's concave down during this whole part, so from like negative infinity up to about 8. Well, the second derivative test tells us where is it negative. It's negative down here. That's where it's concave down. Okay, concave up. Second derivative is positive. Yep, the second derivative is positive. A point of inflection is where it changes from positive to negative, the second derivative. Yep, it changes from positive to negative. So we're looking pretty darn good. Last test that you need to know, which would make sense, if f prime, or the slope, is equal to 0, so we're here equal to 0, and f double prime is negative, meaning we have a concave down, then it's a local maximum. That makes sense. If f double prime is positive, meaning concave up, and f prime at c is 0, that would be a minimum, which makes sense from these drawings here. Okay, I really apologize for my voice. Thanks for hanging in there with me. And sorry for the semi-long video, but it's actually shorter than the first version when I recorded, or I thought I was recording. Anyway, hope you guys have a great night. Bring questions tomorrow. Thanks.